Okay, hi guys, my name is Tohuvavohu. I'm not a member of your University of Arizona community. I'm from the University of Toronto. I'm a PhD student there, but I want to talk to you about a concept that myself and a bunch of other people around the world are trying to work together to build this sort of future of abundance in space telescopes and how we can maybe work together to make that happen. And my vision of this abundance really does look like this. And it's driven, I'm an astronomer. I love doing science, but unlike some of the other concepts that we've heard about today, it's driven not only by the desire to do science, but by the desire to engage the rest of the world in doing science with us, right? There are many reasons why you might want to build a space telescope. We've heard about tons of them today. We hear about them all the time. Our space telescopes are very much driven by their science requirements. Here are just some reasons why you might want to put a telescope in space to do different things. But as astronomers, as planetary scientists, as space scientists, we live and we occupy a very privileged position insofar as the public is very inspired by this esoteric, crazy thing that we do. And I think that as we go to a future of abundant flights and accessibility in space, we also owe that public the ability to engage with us in this astronomy future. And so that places that aren't rich like the United States of America, or institutions that don't have the capacity or the breadth of knowledge and experience that the University of Arizona does, can also participate in space-based astronomy. And in order to do that, we have to make space-based astronomy accessible so that we can inspire everyone. So of course, making it accessible means making it cheaper, right? It's simple. And Daniel, who just gave this great talk, also has a nice slide called the space spiral, where he tries to explain why space telescopes are expensive, right? And it starts with a historical high cost to get to orbit. And that meant that you drove higher cost missions. We operate within a cost cap budget in the US and pretty much everywhere else, unless you're the military. And so that means, if you're a budget cost cap, you have a lower total number of missions if all of your missions are expensive. If you have a lower total number of missions, you have fewer number of shots on goal. So each science community wants their own space telescope. They want to say, oh, I want my IR space telescope. I want my X-ray telescope, and each of them has to be unique. But if each of them is unique and you only get one shot per decade, or in some communities, one shot per 30 or 40 years, you're going to make sure that has very challenging science requirements because you want to make that one shot count. Right? But then if your science requirements are challenging, you have complex missions with no tolerance for failure, and you enter back into the high cost missions and you just go around the space spiral. And this is where we've lived for a really long time. And so what I want to think about is, how do we break the space spiral for astronomy, at least when it comes to modest space telescopes, right? Maybe we're not going to break the space spiral for the one-off James Webbs and Hubbles that we've been building, but there is probably a future where modest meter-class space telescopes are really accessible. And the way that you do that is you look at what industry has done and how they have made their space hardware cheaper, right? And they have basically built fungible space telescopes, right? These are unit space telescopes that they produce en masse, right? And these are companies like Satellogic or Planet Labs. They build space telescopes. The difference in their space telescopes is that they look down, right? But they produce them at scale. Now, astronomers and planetary scientists probably have requirements on our instrumentation that are, significantly beyond that of what you have to do most Earth observation. But I'll posit that is not a qualitative difference. It's just a harder problem. But it's the same type of thing. The way that we solve this is to build non-unique space telescopes. That's what we need to do, right? And Daniel gave an example of building, 50 or 30 or however many it was, 8-meter non-unique space telescopes. Well, we could probably build many more smaller aperture telescopes. And then the question becomes, who wants them, right? You need to have each of those instruments be sufficiently capable and general purpose that it interests a large enough user community. And you need to do that because the demand from the community has to drive the justification to build a large number of space telescopes. And so each of them has to be pretty good, right? You probably aren't going to get something that's good enough to interest a large enough number of people in a CubeSat form factor. But maybe at 0.5 meter, maybe. I've had astronomers tell me, oh, I would never be interested in a general purpose space telescope. And I tell them, well, Hubble is a general purpose space telescope. So there is some line between a 10-centimeter CubeSat telescope and Hubble at which a large amount of our community will be very interested in using that space telescope at a very high rate. And we just got to find that line, right? And that's what we're trying to do. Cool. And so what we've done is put together a worldwide community of people. Many of them are in the audience right now, but also on all the continents except Antarctica, and run a series of workshops to try and address this problem from various different approaches, to consolidate people's science requirements into one or a few concept unit telescopes for mass production. This community is broad. It's not only academics, it's also industry. There's also a number of extremely talented amateur astronomers who are engaged with us because they want a space telescope too, and students. And we've heard, I'm going to give you some highlights of what our community has been talking about. We've heard from NASA thinking about, would they ever be willing to fund a mission that is not necessarily driven by a particular science requirement, but is instead driven by a broad general purpose astrophysics vision and accessibility as a co-equal goal? How we could partner with industry to do this? Lessons learned from an actual operating constellation of 6 identical space telescopes that's been up for the last 9 years. Only 5 of them still work, but that's pretty good numbers in my opinion. How to build this future responsibly, right? If we're going to build a large number of space telescopes, we have to make sure that we're not contributing to the problem that we, complain a lot about by astronomers about not developing space in a productive and in a respectful way and treating our shared heritage of the night sky respectfully. And then from people like Erica and others, different science opportunities that you might have with a vision of many space telescopes, and some challenges that would result from trying to translate the Planet Lab's vision of building many space optics to astronomy. Just one example of how desperate people are for space telescopes, this guy did an amazing science with a meteorological satellite that just happened to catch Betelgeuse right near the edge of the Earth limb when it was dimming. And this is only an example that, people are desperate for space telescopes, and they don't have to be JWST or even Hubble size to do amazing science. And even more science ideas. This one is for a constellation on the top left of 10 or 20. Down here is this a group at Berkeley that's planning a constellation of 200 20-centimeter CubeSat space telescopes to do a full sky all the time microlensing survey array. And then we get to the hardware, right? This is where it really comes down to brass tacks. What's going on with the hardware? We heard from industry how they are now churning out space qualified optics that are currently in orbit in the dozens at least that are public, looking down at us, and how cheap they're able to do this. At the top, that's a 45 centimeter all aluminum OTA that's space qualified, 45 centimeters, half a meter, $1 million a pop, ready to go. What can we do with this type of vision? And then, of course, it comes to operation. If we continue to operate space telescopes in the way we have historically, that doesn't scale well with cost, right? We can't pay $70 million a year for Hubble times 100, right? And so we've been hearing from industry about how they operate constellations at scale, from our most efficiently operated space telescopes about how they do it, and then we dug down into the cost modeling to see if we could ever convince NASA that we could actually pull it off. It's kind of iffy there. But what it really all comes down to is that there's a really rich vision in our community of people who want to build a large number of space telescopes. I'm at the University of Toronto. I don't have the types of opportunities or resources that you have here at the University of Arizona. And so the question was, how can I contribute to this vision? And one thing that came up was that there really wasn't any high performance, low cost UV optical camera system that people could spec for these types of missions to produce at scale. Right? There are these optics that a private industry is making for Earth observation that in many cases are usable for astronomy. The spacecraft, of course, are being produced at scale for other purposes. Launch costs are going down, but the actual instrument package, no one cares about that except the astronomers. And so it's up to us to push on it. And so that's what we've been doing at the University of Toronto, is trying to build a general purpose, low cost, high performance, low noise UV optical camera system and give it out almost for free to the rest of the world. And so this is our team at the University of Toronto. We're called the Loves team because we built a mission concept a few years ago that was based around these ideas called the Little UV Surveyor, but we don't do that anymore. It's engineers, grad students, professors across 3 different units at the University of Toronto. And we're developing this camera system that has very good performance from 200 nanometers all the way about to 0.9 microns. And it's a large format, backside illuminated scientific CMOS sensor with low noise and good performance, PQE of like 93% at 600 nanometers and better than 30% QE all the way down to 175 nanometers. I just don't have it here. And we've been characterizing and qualifying these sensors for the past few years. It's passed radiation testing. We've even dosed it to what it would experience if it did a flyby of Io in the Jupiter system, and these are really good sensors, and we've built an electronics package around it to try to build, see if we can do this. And critically, these sensors are cheap. These sensors were developed for biology on the ground. They just happen to be really good. And so we found that and we tested it, and it turns out that the vendor's claims are true, and so we're going to package it for astronomy. And real friends give you space on their spacecraft. So despite all this qualification, right, no one's going to believe that we can deliver a high quality UV optical space camera for, order $30,000, $40,000 until we actually show that it works in space, no matter how much TVAC and rad time we have on the ground. And luckily in early December, our friends in Europe said, hey, wait, I have some spare space in my CubeSat, which is just a crazy idea to me. How do you have spare space in your CubeSat? If you can fit, you can fly. What they said to us. And so we've been on a sort of a rampage trying to meet this launch opportunity. And we're astronomers, so we want to make it even harder for ourselves. Like, can we even fit a telescope in this tiny little thing? And the answer is maybe. So we're going to put a tiny 2-centimeter optic. It's actually smaller than our sensor. The optics are smaller than our sensor in this situation. And we're going to characterize and show that our camera operates on orbit with good noise performance in a way that scales in terms of its lifetime. And we're also going to take UV images of the sky. And we're going to take the first UV images of bright stars since 1973 and do an all-sky survey of the stars brighter than 8th magnitude and actually all the way down to 12th with this tiny UV camera. And in the meantime, show that we can build it. And we're going to build 4 at once to show that we can actually do this in a productive and scalable way. And our qualification and testing bench is almost fully automated. This is what our optics looks like. I'm just going to pop through it. We're going to do some science. This is what the current design looks like. It fits into the CubeSat right here. We have a radiator plate. We have our optics. We have our FPGA PCB board coupled to our sensor PCB board via flex cable. And the cost target is, a few tens of thousands of dollars. And we're building a bunch of them at once. And we're going to jump when this launches on whenever Ariane 6 launches. So cross your fingers for me. It doesn't explode, but again, the fabrication cost is very low, so that's okay. We can just try again. And we're gonna try to send it up and jump immediately to TRL 7 or maybe 8 if you stretch it. And then it's being spec'd for a European mission. This is a 30 million euro class mission called QVIC, which is a 35-centimeter aperture UV telescope with 2 simultaneous UV channels. And 2 of our cameras will sit at the focal plane. But as I said, we're building a bunch of these. So if you want a UV optical camera and you have a great idea on something you would want to do with it, whether it's some idea you have already or a mission that you want to design around it, let us know and we're happy to partner with you and hopefully we can build this future together. Thanks.
It seems to me that your ultimate goal is to basically create a commercial space telescope that people can buy off the shelf at reasonable cost, anyone, and then operate it and look at things whatever they want as a general observatory. Is that a thumbnail sketch of your ultimate goal here?
Yeah, I would say that is one way to get to the goal. We are building this camera without any ITAR or ER, and it's going to be open source hardware and software. So really my goal is to empower other people to build it, like a hack-a-day kind of project, except there your hack is a space telescope when we give you all the instructions. But you could imagine spinning out a company that builds them, sort of like a plane wave optics for space telescopes. This is something that we've considered, but we really want to enable, let's say, a university in Egypt to engage and build a space telescope and not have to pay all of the money in tech development and instead start somewhere good.
Sorry, just a few questions. I thought you were coming to me. Sorry. Who makes the detector, the SCMOS?
Yeah, so of course we don't have a foundry. The detector is made by a Chinese company called G-Pixel, and it was originally made for biomedical imaging, and now we're flying it in space.
What temperature are you operating it at, or do you envision?
So this tech demo, because it's small, we'll be operating it at 0C, but in the QVIC mission here, it's going to operate at -30.
And do you use SpaceWire? What kind of interface do you use?
SpaceWire and camera link, both options. Yeah.
Nice presentation. Can you hear me? Okay. So you mentioned this sort of in like a throwaway slide about being responsible with large amounts of satellites going up. But can you speak a little bit more about that? Because especially if it's like, oh, any university can put up this thing, even if there's like a pretty high rate of success, like, is it worth, like, what's the impact of having like hundreds or thousands more telescopes
Yeah, thanks for this really good question. I think it's something that we have to take really seriously. I'll first it might sound flippant, but no matter what we do in astronomy, we are not going to make more than a drop in the bucket compared to what the commercial industry is going to be doing and is currently doing. Right? They have 4,000 Starlinks flying right now, or some number around that. But that being said, we should practice and demonstrate the way to do this and develop correctly, or else we have no standing to complain. I think, there are people, for instance, like Aaron Boley, but other people at SatCon that are thinking really hard about how to do this. I think in reality, as astronomers, we'll probably have to move eventually most of our instruments to L2. That's what I think. In order to do that, there'll have to be much more infrastructural support. The comms support will have to be much greater. Everything will cost more, but I don't think there's really a way to continue to develop the LEO ecosystem if we want to take this seriously in the several decades time frame. In the meanwhile, there is a good way to fly these things, right? You can develop, as long as you, like, for instance, if you take into account the MTF of your reflectance spectrum when you're designing your space telescope from the very beginning, instead of putting a visor on it or changing the coatings, and you make sure to operate it in particular orbits that aren't illuminated by the sun for so long after dusk. I think there are ways to mitigate, but at the end of the day, I just think we're gonna have to go somewhere else.
Okay, thank you.